What's up guys, today I'm going to explain you how can we solve this problem known as find the town judge. It's this problem from lead course May challenge. Let's read through the problem statement. In a town there are n people labeled from 1 to n. There is a rumor that one of these people is secretly the town judge. If the town judge exists, then the town judge trusts nobody. Everybody trusts the town judge. There is exactly one person that satisfies the properties 1 and 2. You are given trust, an array of pair trust I, where a comma b represent the label A trusts the person label B. If the town judge exists and can be identified, return the label of the town judge, otherwise return to -1. Let's see the example. N equals to 2, trust equals to 1 comma 2. That means 1 has a trust on 2 and 2 does not have any trust, so 2 has to be the town judge. In the second example, 1 comma 3 and 2 comma 3, there are two trust relations. In the first one it says the 1 has trust on 2, 1 has trust on 3, and the 2 has trust on 3 as well. But 3 does not have any trust, so 3 is following both of these property for being the town judge, and hence it is a judge. However, in this third case, there is a relation for 1 to 3, then we have 2 to 3 as well as 3 to 1. So each of them is trusting some other guy, so there is no town judge, so it has to be -1. It has to return -1. In the fourth example, we have 1 to 2, 2 to 3. That means there is this guy 3 who does not trust anybody. But then what's the problem with this? That everybody else has to trust this guy. However, 1 is not trusting this 3. That's why, and in this example we don't have any town judge. In the last example, similarly, you can draw and see that 3 does not follow anyone, but everyone else does follow 3. So basically 3 is not following anyone, as you can see, and it is followed by 1, followed by 2, it is followed by 3. These are the input constraints. I have already solved this problem. I'm just going to explain you how can I solve this. So basically, just to take care of the edge case, if there are no trust given, then in that case we need to only return 1 in case if there are only 1 people in the town, and that has to be the town judge itself. If there are multiple and we don't have any we don't have any trust relation, that means we don't have any judge as well, so we need to return -1. In the rest of the cases, let's see how did I proceed. So I have created a set, an ordered set, to keep track of unique elements, and then also I have created index and outdex. What these index and outdex map contain is the number of incoming edges and outgoing edges for each node. So basically, just to give you an explanation, we can treat this as a problem, a graph related problem, where one relation is representing an edge going from 1 to 3 in this example. Similarly, here we can say there is an edge going from 2 to 3, then we can say there is an edge going from 3 to 1. So each node will have certain amount of in degrees and certain amount of out degrees, and the judge, as the first property says, just trust nobody. That means there is no outgoing edge from the judge, and everybody else has to trust the town judge. That means there has to be an incoming edge for judge from everybody else. That means the out degree of judge has to be 0, and the in degree of judge has to be n-1. Why n-1? Because apart from judge there will be n-1 elements, n-1 people. So what I have done is simply scan through the trust relation array, and for each relation I have added out degree, incremented the out degree and in degree. Also, to take care of each unique element, I have inserted those first and second element of the each trust in my LMs set. When I have scanned through it completely, I need to just scan through my unique elements and find if there exists any element. That means if there exists any value which follows the property of town judge, we need to return that element in the end. If we don't have any such property, if don't have any such element which follows this property, we need to return -1. So yeah, as you can see, the solution is already accepted. So yeah, the time complexity here is O of n. If we consider that the maps are taking constant time for lookup and insertion, and the space complexity is O of n as well. Thanks guys for watching this video.